Hello, so we will discuss problem rank queries of starters 94. It's the third last problem in the div 1 and it's relatively easy for a div 1. As you can see, almost everyone has solved it. So let's get in the problem. The problem says that you are given an array and for each element of the array you have defined the rank. Rank is simply the number of elements which are strictly greater than that element plus 1. For example, if we take this 3 here, the elements which are greater than this is 4, this 5, this 4 and this 6. So its rank will be 4 plus 1 equals to 5. Okay, and elements can have the same rank. For example, this 2 and this 2, they both have the same ranks because they are the same numbers and they will have the same elements greater than them. All right. Now, the question says that you in this original array, right, you are given some queries and you have to answer those queries. The query is of the form of k comma r. K defines the index. So let's look at this query, which is 1 comma 2. So the first, based on one based indexing, this is the first element. And R is the new rank sort of thing that we want to obtain. So what we actually are doing is, when we are given this element AK in the original array, we can choose an integer X. Okay. And what we can do is we can delete X elements from here and X elements from here independently, like total 2X elements, but X elements from the right, X elements from the left. After that, the new rank of this element AK should be less than equal to R. This R is given to us. Okay. So if we just look at the example queries, if this is your original array, this is Q, and you have to find the minimum X. Okay. Like obviously, if X is equals to infinity or very large, um, every element in the array will be deleted and the AK value will be 1, which will be less, like R I think has a maximum limit of 1, like minimum limit of 1. So obviously we can always find some X, right? But you have to find the minimum X which answers this setting. So for example, this query, this is the first index. This is the right portion, this is the left portion, which is empty. And you have to find the minimum X such that the new rank is less than equal to R. Okay, not exactly equal to R, less than equal to R. So uh, the current rank of this 2 is 3 because 2 is less than 3 and 2 is less than 4. And if we add 1 to that, that will be 3. So if we just put X is equals to 1 and we don't delete anything from here, like we can delete at most X elements. So it's also not necessary that we have to delete exactly X, right? So from this is empty, the left region, so we don't have to delete anything. From the right region, we can delete this 3 or we can also delete this 4. But we cannot delete both because X equals to 1. And then the new array will look something like 2, 1, 4. Suppose we delete this 3. So then the rank of this element will be 2 because only 4 is greater than S. Okay. Anything, if X was equal to 2, then also, and we suppose we deleted this and this, the new rank would be 2 because of 2 will be 1 because no, it will be number of elements greater. Yeah, it will be 1. So because the new array will look like 2 and 1. And there's nothing greater than this, and the rank will be 1 plus 0, which will be equal to 1. But X equals 2 is also an okay thing, but X equals to 1 also satisfies the thing they're asking, and this is the minimum. So we will return 1. Similarly, for the second query, um, just a second, let me erase this. In the second query, you are given k equals to 2, and you have to make its new rank less than equal to 1. That means if you look at the left and right region, suppose X was equals to 1, right? If X was equals to 1, then what you could have done is you could deleted one element from the left, which is this, and maybe one element from the right, which is this. But after that, the new rank would not be less than equal to 1, which was asked, right? The new rank will be, in this case, 2, because 1 has 4 or greater than it, and then 1 plus 4, 1 plus 1 equals to 2. So X equals to 1 will not work here. X equals to 2, it will work because here there is only one element. You can delete at most 2. You delete this, and from here you delete the two elements. And then there is nothing greater than this, so it will be 0 plus 1 equals to 1, which will be the new rank. And then x equals to 2 will be the answer. Also, x equals to 3, x equals to 4, and all the way till x equals to infinity will also make the rank equal to 1, but uh, they will be greater values and they are not uh, uh, optimal. Okay, so let's move on to the solution. Also, each query is independent, so the array doesn't change. Okay. Suppose the query comes from for this element I with some value r. There is some region to its right and there is some region to its left. Okay. The rank is only affected by the elements which are greater than a of I. Okay. If you delete those elements, then the rank will decrease. Okay. So it is always optimal. Suppose you choose some x and you want to delete some elements from the right and from the left. It is always optimal to delete only the elements which are greater than a of I. Because by deleting any element which was less than a of I, any element which was suppose k which was less than a of I, the rank of ith element will not be affected because the rank is only affected by the greater elements. So we will always greedily try to find x greater elements in this region, x greater elements in this region, and then we will delete it. Okay, that will give us the most reduction in the rank. The second thing is, if after deleting x elements, suppose for this AI you found some x, uh, and then after deleting x elements, at most x elements from the right and from the left, the new rank is less than equal to r. Then it is obvious that if you deleted x plus 1 elements, then the rank will also be less than equal to r, because then you will be deleting more elements. Okay, so for example, in these examples that I told you, right, that um, for example, for the query for this array 2134, and for the query let's say 2 let's say 2 comma 1, right, for this element you want the rank to be less than equal to 1. X equals to 2 was the answer, right? X equals to 2 was the answer. But x equals to 3 will also be, uh, the rank here will be also less. It will be either less than x equals to 2, or it will be equal to the rank at x equals to 2. Because here you have more options to delete from the left and from the right. So you can, if there were some extra elements which were greater than a of I, which were not deleted uh, before, for some greater x, you have the opportunity to delete them. So in that case, your rank will always reduce. So if for some x, the rank of a rank is less than equal to r, then for some x greater, some new x which is greater than this, the rank will also be definitely less than equal to r. So by this statement, what I'm trying to say is that we can simply binary search on x. Okay. So suppose this was our AI, and there were four elements which are greater than it to its right and two elements greater than it to its left. And suppose you want the final rank to be less than equals to 3, and you want to find the optimal x for that. Um, you can simply binary search on this. So suppose you choose x equals to maybe 5. Okay. So from the right region, you will delete uh, at most 5 elements. From the left region, you will also delete at most 5 elements. But here there are only 2 and 4 elements, so everything will be deleted, and its new rank will be equals to 1. So for x equals to 5, the rank is equal to 1, which is less than equal to 3. So if we now increase x, the new rank will again be less than equal to 3, and that is not optimal. Like, I mean, we have already got our answer at x equals to 5. Why do we want to search ahead? So we will search in a lower range. Uh, so like we added the start is equals to 0 and end is equals to maybe let's say 10, and then we are binary searching on it. So our mid was currently 5. So we search for x equals to 5. Then we search to the left. So maybe our new mid goes to 2. Then we check, okay, is x equals to 2 an answer? So if x equals to 2, you delete two elements from here, that is you delete these two, and you delete two elements from here. So you're left with two elements. The new rank will be 3, and which is also less than equals to 3. So mid equals to x equals to 2 is also a good answer. So then there is no point searching ahead of 2. So we will just search to the left again. So we are just doing normal binary search. Then we'll check, okay, is x equals to 1 an answer? So x equals to 1 is not an answer because um, you had like two elements here and four elements here. So you delete one from here, you're left with only one. You delete one from here, three. So the new rank will be, I think, 1 plus 3 plus 1, which is 5. So x equals to 1 is not the answer. So x equals to 2 will be your answer. So this is how you binary search, and for each query you can um, find the optimal x. Also, if you are subtracting x from here and subtracting x from here, the new number of elements which are greater than a of I will be um, max of 0 comma right greater minus x plus max of, this is something just to keep in mind, okay, when we are writing our code. Like if you're deleting x elements from here, you are only deleting the greater elements. They only affect the rank. We want to find that after deleting x from here and x from here, what is the new number of greater elements? Because that is how we calculate our rank. So this is the formula for greater elements. All right. So I hope till this it is clear. Simply by searching for x. Now the only problem which arises is that for each AI, how do you find this right greater and how do you find this left greater? Because once that is found, then everything is very simple. Okay. So this is a sub problem which first of all you should try to solve on your own. And now I will explain how I did it. Okay. I might have overkilled it. I used segment trees to maintain the like to do range queries and to determine how many elements are greater than a of I. So what I did is number one, I sorted the queries. Okay, first before doing this, first what I did is for each AI, I found what are the total elements in the entire array which are greater than a of I. Total elements greater than AI. There are multiple ways to do it. Number one is you can first initialize a segment tree, update it. So for each I, you update the segment tree with a of I at index I, and then you update the segment tree at a of I with the value 1. So you add 1 there, and then when you want to find this, right, you simply for each I greater of I is equals to just query the segment tree in the range of ai plus 1 to infinity. Okay, just query in that range. So that is how you can find a total number of greater elements, and I have stored that. Okay, now once that is done, I will sort my queries. Okay, and suppose this was my array, right? Suppose this was the query that I had just encountered. I had encountered the query for some a of k plus 1, and I have solved this query somehow. Now the next query is somewhere here. Okay, somewhere here. So what I did is I maintained, this is a second segment tree, so I maintained another segment tree which stored information to the right of the last query. Basically, when we want to find for any, for example, in this element, if you want to find this number of elements which are greater than its to its right, suppose you maintain a segment tree which stores information about all the elements in this range. So what you can do is you can then simply query this segment tree for the range of ai plus 1 to infinity to find the number of elements which are greater than it. And these elements will be greater to its right because segment tree only stores the right hand side information, nothing about the left hand side. So when I have answered this query, right, what I will do is I have sorted the queries based on the uh, index and descending indexes, like from right to left. So like if the indexes of the queries were 1, 2, 0, 5, so I sorted it and it was like 5 to 1, 0. Then I answered them in this order. So this was supposed corresponding to index 5. This was supposed corresponding to index 2. So now when I have answered this query and I'm coming here, I will update the value of index 5, the value of index 4, the value of index 3. I will basically update these three values in the segment tree, and the remaining portion was already present in the segment tree when I was solving for this query. So this is how the segment tree will you will maintain the ranges to the right, and when you suppose then you answer another query ak minus 1, so you basically um, add these indexes to the segment tree, and then this entire region was already present. So this is how the segment tree maintains the information only to its right. Then after finding RG, you can find the left greater equals to the total greater minus RG. And the total greater we had already uh, found out. Okay. Once this information is found, then the question becomes very simple. You just have to do the binary search on X, and I already told you that for a certain X, what will be the new number of elements remaining. So this value plus 1 should be less than equal to R. If it is, then you will search for a lesser X. If it is not, then you will search for a greater X. Okay. Then last thing, if you have understood till here, why did we sort the query? We sorted because that way we could uh, constrain our problem, and just since we knew the previous query was to our right, then we are coming to ourselves. We are just adding these additional points to the segment tree. Okay. The last thing is that in this question, AI is in this range. AI is in the range of 1 e की power 9. So you cannot make a segment tree of such a big size. What you need to do is you need to perform coordinate compression. So perform coordinate compression on all the elements in this array, right? On all elements in the array. That way the segment tree will then be proper, because n is equals to 2 into 10 to the power 5. So the segment that big of a segment tree you can create. And why coordinate compression is working? Because you're only concerned with the greater and lesser elements, right? So like we know, suppose this was your array originally 2, 3, 6, and 5. After coordinate compression, it will become something like 0. This will become 1. This will become 2, and this will become 3. So the relative ordering remains same. The if this index is less than this index, then this index is also less than this index. So the answer will not change. I will now I will first just summarize everything. So number 1, sort the queries. Number 2, perform coordinate compression. Then for each AI, find left greater and right greater, and then just binary search on X. Okay. Now I will show you my code. So 1 second. All right. So this may look a little bit complicated, but I'll explain it. It's very simple. So this is your array. This is the coordinate compression. So I just kept a track of all the elements in the array, and then I assigned them some indexes. So now they are mapped from the range of 0 to n minus 1. Then this is the queries. We take the queries, we push them in the vector. We then sort the vector in descending order. The segment 2 basically is needed to find the total greater. So what we do is we do an initial uh, traversal on the array. We update the segment tree, and then how do I show? Okay, then when we are solving the queries, right? When we are solving the queries, our right greater will be um, this, or in this first segment tree is what is needed later on. This stores the information to the right. So basically, we just query the segment tree from index array of I plus 1 to the maximum possible, and these are compressed coordinates. And the left greater will be the total minus right greater. The total is from the segment 2 that here we updated. Um, I will explain this line in a bit. Then we just, this is start and end are, mid is basically the value of x. The new greater we check if that is less than equal to r. If yes, then we update the answer, and otherwise we go ahead. This line basically adds the new data points to the this segment tree. So while the left index basically is the index that has not been added in the segment tree. So while that index is greater than the current query's index, we will add that index's value and we will update it. Finally, we will print the answer. The complexity, each query, I think you're solving in order login, because this takes login time, and then this is also login separately. And then you have q queries, so it's like order q login, and then there's n login for this. So it's usual order of n plus q login. So the complexity will be order of n plus, I think, q login, which is almost like order of n login. So this is fine. All right. Thank you for watching the video. I will see you in the next one. Bye bye.